If we want to estimate the um, population parameter, and we don't have a full census of the entire population, we can take a sample and calculate a statistic, which will give us an estimate of the population parameter we're interested in. For instance, if we're interested in the average income for all US citizens in 2020, we could take a sample of 300 US citizens in 2020 and look at their income. And the mean of that sample would be giving us some kind of estimate of the population parameter. But the random sample could have come out differently, and so our estimate could have been different as well. And the main question that we want to examine is how different could the estimate have been? Can we get some kind of handle on the variability of the estimate that we're looking at? The estimate that we're looking at can be thought of as the true parameter plus some kind of error, and we'd like to somehow bound the error or get some kind of sense of what the error could be. It would be really helpful if we could get another sample. If we could take many different samples, we could try to understand how the statistic changes in each of the samples, how our estimate is going to vary across different samples. The problem is that it's very expensive to go out and resample the whole population. It can be expensive. It can also take a lot of time. So how can we get an estimate of the variability of the sample without having to go back and sample from the population again? The idea that comes to our rescue is called the bootstrap. The bootstrap is a technique for simulating repeated random sampling. All that we have is the original sample, which is large and random. So it probably resembles the population. We can't sample again from the population, but we could sample from our original sample. That's going to be the idea of the bootstrap. In the bootstrap, the original sample that we take looks pretty much like the population. And each of the resamples that we take is going to look pretty much like the original sample. If we had 300 observations in our original sample, then each of the resamples will also have 300 observations. But they won't be exactly the 300 observations in the original sample, because we're going to sample from the original sample using replacement. So every time we select an observation in our sample, we're going to put it back so that it could be selected again. Some observations will be selected multiple times. Other observations in our sample won't be selected at all. And that's going to give us the variability across the different resamples that we have. So here's what we wish we could get. We wish we could get the population statistics completely. In that case, we'd have a census and we could actually calculate the parameter directly. Instead, we get a single sample, and from that single sample, we'll compute many resamples of that sample. For instance, we might compute, say, 10,000 different resamples. This is cheap and computationally efficient because our computer can just churn out a bunch of resamples very, very quickly for us. For each of those 10,000 resamples, we'll compute the statistic that we're interested in, maybe the mean income. And so then we'll have 10,000 values of that mean income, and we can construct a histogram of those 10,000 values. So the key to resampling is that from the original sample, we'll draw at random with replacement, which is crucial, as many values as the original sample contained. The size of the new sample has to be the same as the original one so that the two estimates are comparable. Okay, how do we use these 10,000 resampled statistics to compute a 95% confidence interval for the parameter that we're interested in? Well, we expect the bulk of the histogram to lie over the correct parameter value. For a 95% confidence interval, we'll split the missing percent, the missing 5%, into 2.5% and 97.5% percentiles. So we'll throw out the bottom 2.5% of our statistics, and we'll throw out the top 2.5% of our statistics. That leaves 95% of our statistics, and we'll use these values as the endpoints of our confidence interval. In general, to get a p% confidence interval, what we'll do is we'll subtract p from 100, we'll divide by 2. That will tell us how many percent of the data we need to throw out on either side of the confidence interval, and that will produce for us the correct confidence interval that we're looking for. Let's look at a demonstration of this in the IPython notebook. Let's give an example of bootstrapping on the San Francisco incomes. First, we define a bootstrapping function called bootstrap median. It takes 3 parameters as input values. The first is a table containing the original sample. The second is the label of the column for which we wish to compute the medians. And then the replications is the number of bootstrap samples that we want. We make a empty array called medians, and then we loop replications number of times. And in each replication, what are we doing? We're first computing a sample from the original sample. And this sample, the default is to compute a sample of exactly the same size as the original sample and with replacement. So the bootstrap sample will be the same size as the original sample, but some of the original samples observations are repeated and some are not shown at all. Then we compute the resampled median of the column that we're interested in, and finally we append that resampled median to our list of medians, and then we return the whole list of medians. Here's an example running the bootstrap median function. We've got our original sample of 300. We're interested in the total compensation, and we'll bootstrap 1,000 times. I've already run this offline because it takes maybe about a minute to compute all of the 1,000 bootstrap medians. But if we're interested then in trying to find how the bootstrap median compares with our population median, we might just run the population median computation again, and remember that the population median was $107,518 for the San Francisco employees. And here's a histogram of the bootstrapped medians. This is the histogram of the 1,000 resamples, and there's the actual parameter value. Of course, we never really get to see the actual parameter value, but here we happen to know it. To calculate the left endpoint of a 95% confidence interval, we compute a 2.5 percentile of the bootstrap medians. That's just a bit over 100,000 in this case. And to calculate the right endpoint of a 95% confidence interval, we compute the 97.5 percentile of the Bootstrap medians. This means that we have 2.5% that we're throwing away on the bottom of the collection of medians and 2.5% that we're throwing away on the top of the collection of medians, leaving 95% in between. Here, I've just redrawn the histogram, but also I've drawn in yellow the confidence interval that we computed.